I'm Bruce Tolley, Vice President of Technical and Solution Marketing of Solarflare, and I'm here today with my colleague from CloudFlare to talk about how to make the web faster and safer. So a little bit about who Solarflare is. Has anyone in the room heard of us before? So we are a networking company. We do software and hardware, focusing on 10 and 40 gig Ethernet. We also have an application acceleration stack, branded Open Onload. We started selling a lot of solutions into the financial trading space. So does anyone in the room not have a 401k? So if you are invested in the market, either in the USA, Europe, or Asia Pac, your equities or options are being traded across Solarflare equipment, software and hardware. So we're in NASDAQ, we're in NYSE, we're in Deutsche Bank, Deutsche Börse, the Hong Kong Stock Exchange, multiple exchanges and trading companies throughout the world. So recently, though, we've been branching out for the last 4 years. We've had CloudFlare as a customer. They raised over $100 million this week, or at least they made the announcement. I think they did the fundraising earlier. We've got multiple POCs and engagements with customers worldwide, especially in Europe and the Eastern Seaboard. We won DigitalOcean a few months ago. Does anyone do their software development on DigitalOcean's network? Anyone in the room? Well, they claim to be the #2 cloud vendor next to Amazon. And I say China here, so when I wrote this last week, I was hoping that we'd get a big order from Baidu. Does anyone in the room not know who Baidu is? So Baidu is going to start to buy tens of thousands of servers. So if you haven't heard about us before, now you know who we are. So what do? We help our customers optimize application performance from the app down to the wire. We've been doing that on Wall Street since 2009. We've been doing it at places like CloudFlare here in San Francisco and worldwide, and LeaseWeb and DigitalOcean more recently. How do we do that? We do it with a user-level networking stack, sometimes called OS bypass. So if you're familiar with DPTK or InfiniBand, technologies like this, we have this as a solution in our toolkit. It's fully hardened, so it's deployed in tens and thousands of nodes worldwide. These networks I talked about, especially at NASDAQ and NYSE. We support BSD sockets, so it's a industry standard socket facing your application. So there's no need for our customers to change their applications to run onload. It's TCP and IP and Ethernet on the wire. So if you need to support multicast, firewalls, do TCP IP, traffic engineering, all that just works with Open Onload. It's also open source, so we have customers that take our code and then we never talk to them again. We have other customers that post updates back to us, bugs as well as bug fixes. We also have a hardened enterprise version that we sell 24/7 support on. It is, of course, Linux. We support Red Hat, Ubuntu, SUSE, any variation of Linux you name, we support. So we have many other libraries, interfaces, and toolkits, so I won't spend too much time on this slide. But we have a low-level interface we call EFVI that's very similar to DPTK, but it's much simpler and easier to use, and we believe more performant. We do have support for DPTK on our roadmap. Has anyone in the room deployed DPTK today? So we're seeing a lot of interest in this, especially in the telco environment in Europe and Asia Pac. But unlike DTPK, Open Onload, it has a full standards compliant TCP IP stack, and it presents a standard interface to the application. So we have a lot of customers that love it. So today I want to talk a little bit about what we can do with our user level networking to accelerate NGINX. I and other members of my technical team have been in conversations with NGINX for many months now, and in some ways they were a continuation of conversations Solarflare was having in 2009 and 2010 with a company called Zeus. So Zeus did a software-based load balancer. It was acquired by Riverbed and then sold to Brocade quite recently. But we knew the Zeus team quite well, and many of those folks are back as employees at NGINX, so we're happy to see a happier home for them. So what we've been doing is figuring out how to accelerate NGINX with our user level networking stack. A lot of our customers, they default to Intel because it often comes free with the server. So this is a performance slide showing you the top blue line is what you can get out of our open onload stack. The golden line is our Linux kernel. So this is Solarflare's Linux kernel that's distributed in box in SUSE, Canonical, Ubuntu, as well as Red Hat. And then the lower line is Intel. So you can see that we scale and perform much more highly both in the kernel as well as our onload stack than Intel. And we do this with onload by supporting things like, of course, user level networking, OS bypass, as I explained before. We've also enhanced our support for active and passive socket caching. And if you want more technical information on that, come by our little booth out here. And then we've built in, with the guidance of the NGINX team in the last few months, support for SO reuse port. There will be a presentation later today from the Intel folks, I think, about that. But it's supported today in Linux, and we built support for that into our onload. And this is a kind of performance you can see today with the onload we're shipping. So that first slide was static HTTP NGINX connections, both the open source and the commercial NGINX Plus version. This next slide is looking at long-lived connections, simulating a video on demand stream. So I have here both 40 gig and 10 gigabit. The 40 gig is up and to the left, and the 10 gig is down and to the right. The 10 gig we actually bonded. I used link aggregation to create a 20 gig full duplex link using LICP. So once again, you can see that Solarflare scales. The blue top line is Solarflare, and the bottom red line. Where the line's flattened is actually the limit on bandwidth of the link. So ultimately, these systems will be throttled by how much network bandwidth is available. So if you're connecting at 40 gig, no matter how high the performance of the system could be, in theory, it can only perform up to 40 gig, since that's how fat the pipe is. So you can see that we're scaling more quickly and supporting a higher rate of connections than Intel, and also filling the pipe using fewer cores. So we talk about this as an efficiency metric. If you want to use those very expensive CPU cores for other work, you can do that by using open onload. So what other kind of efficiencies can we help our customers with? So does anyone in the room care about power and how much power costs and cooling? So 2 or 3. I imagine most of you are more on the development side, but someone in the company needs to care about power. So these are some recent power numbers that came out of my CTO lab. This is on a Dell 610 server using a sensor that comes inside Dell called IRAC. There are other ways to measure power. Google's been rather prominent in evangelizing their Google power meter. I used to be in Boy Scouts with this guy who worked in the hardware group at Google, and he was always talking about power meters and measuring every device in his house. There's also Spec Power, a standards-based sensor that you can pay checks to. They're based out in Europe, funded by the EU. But here we use something that came for free, the Dell IRAC sensor. And if you look at the 2 rightmost columns, I divided the Solarflare onload number by the Intel number, and you can see that we're almost 98% more power efficient than Intel. And although if you look at the spec sheets of some of these parts, the Intel rated power consumption for their NIC is a little bit lower than Solarflare. We also noted in this work that without a workload, with the machine at rest, both machines were still consuming 70 watts. So there's a lot of more work to be done here, but we were very happy that with this finding to see that we are much more power efficient than Intel for those folks who care about power. So some load balancing numbers. So I know that load balancing is a pain point for many customers we talk to out there in the marketplace. I got this data yesterday and built the slides last night after the lovely dinner NGINX served to us. At least I thought we were going to get dinner, but it ended up being sushi served on little tiny plates. So we're seeing, I have very different loads here, 1 kilobyte, 100 kilobytes, and 10 kilobytes. And the cores is the horizontal axis. So once again, you're seeing that as you increase the core count, of course there's more work that can be done by the cores. The Solarflare green line scales to 4 to 5x that of the Intel line. The Intel line is pretty flat. So if you're in need of higher performance on your load balancers, come talk to Solarflare. So in summary, before I turn to the next presenter, so we can help you increase performance of NGINX, the applications running on NGINX, 2x to 4x, depending on whether the use case, whether it's HTTP static, serving up static web content, and the highest bump we saw was in load balancing. Also, if you or your operations people are concerned about electrical power consumption, we can help you with that. More information is on our website. We've got many technical reports you could browse at your leisure. So now I'm going to introduce the next presenter, John Graham-Cumming. He keeps correcting me on how I explain his title, but I think he likes to be presented as the software guy for CloudFlare. He's been a computer scientist active in the industry for many years. At one point in his career, he worked for a company that built token ring devices, but I won't hold that against him as an Ethernet guy. CloudFlare has been a very important customer and partner and given us a lot of ideas for developing our roadmap. So please give a warm welcome to John Graham-Cumming.
Cheers. Yeah, as Bruce was saying, CloudFlare uses Solarflare cards in all of our servers. And just to give you an idea of what CloudFlare does, so we are the server that your web browser connects to for a very large number of websites, about 4 million websites. Many of them very well known. So if you visited Reddit, you hit one of our servers somewhere around the world. And we do caching and acceleration of the web content using NGINX. So we have NGINX in every one of the machines spread around the world. And I've now lost count of how many locations we have machines. This is the latest map showing them around the world. The idea is that there is always a machine close to the person who's got a web browser, be they on a mobile network or be they on an actual computer. And we use a technology called BGP Anycast, which means that if you go to a website that uses Cloudflare, then you will get the same IP address no matter where you are in the world, but you will automatically be routed to the nearest machine. And the idea there is that we are building a network that should be 10 milliseconds latency away from everybody who's on the internet. That's why we have that huge number of machines around the world. And the reason we want to do that is because we want to fight against the speed of light. If you look at a TCP connection, one of the big things you're fighting is the latency between the client and the server itself. And because we have these caches around the world, acceleration points, we can do that. To give you a sense of how far 10 milliseconds is, in fiber from London, you get halfway across France. So we're trying to cover the world in little circles like that. And we're very, very close to doing that for the entire internet using population. Now the problem with being 10 milliseconds away from everybody else is you've suddenly created yourself an optimization problem. Because now, if you want to get any speed, you've got to do some pretty significant speed ups. And you have to now look at everything from your hardware up in order to do it. So at that, 10 milliseconds, if you want to squeeze out a millisecond, you're talking about 10% of the number you're dealing with. And so what we had to do was look at everything from the NIC up all the way through NGINX. And so for that, we use Solarflare. And that's been great, and it's worked very well, and what Bruce has talked about is all true. But one of the problems we have is that people don't just use our websites, they attack them. And they attack them all the time. So one of the things we run, as well as the HTTP side of things, is the DNS for all these websites. So we have an enormous number of DNS servers around the world, and of course if you want to make it fast, you want the DNS servers near people so they get an answer quickly. And a quiet week on DNS, which for us almost doesn't exist, would look something like this. Requests come in, at some pop, depending on when the sun is up, there'll be requests because people have gone to bed if the sun has gone down. Pretty normal in and out. Unfortunately, what it often looks like is this, which is a huge amount of incoming traffic, almost all of which is bogus, and a small amount of outbound traffic where we're trying to respond to legitimate queries. So we have a big problem of how do you pick out of that the legitimate things so that people can get to Reddit or whatever site they want, and how do you throw away? And so we actually use Solarflare and NGINX in combination to do some of those things. To give you a sense for us, a low-end attack, one that really isn't very interesting, there'll be one legitimate packet in every 1,000 hitting us. And you want to pick that one out and actually respond to it. When it actually gets busy, when the SRE team starts really worrying, you're talking 1 in 10,000. So a very typical, and that's very typical, 1 in 10,000 packets. So you're having to receive these packets and make a very, very rapid decision about, is that something I need to throw on the floor, or is this something I actually need to respond to and pass up the layers? Just to give you a sense of this, I'm going to talk a little bit about attacks on DNS. The same thing happens in TCP with SYN floods, the same sorts of things, but I'm going to take you through some different scenarios. So the most harmful scenario is that our connection to the internet is congested, right? You manage to fill the pipe that we're paying for. And there's really not a lot you can do about that other than start blocking really brutally IPs, buy more connections, make the pipe bigger. That doesn't happen that often, and it certainly hasn't happened recently to us as we've scaled up. So we really then get into, okay, we've got this flood of packets coming into a point of presence, what do we do with it? So at the router, so there's a router in each POP where the connection comes in. We can pretty easily filter 10 million packets per second without a problem, but we're using quite brutal filtering mechanisms there. So that could be IP, the protocol like drop all DNS, which of course isn't a very good idea, and sometimes even packet length. You'll see some people saying, we'll just drop everything that's length 73 because the attack traffic is all 73 bytes long, for example, which of course has collateral damage. So we don't really like doing that. We also use a technique called ECMP. ECMP allows us, once something has come into the router, to spread it across the servers that are inside. So what we'll do is a flow of traffic is coming in, and then rather than hitting an individual machine, simply it's a hashing algorithm run by the router. We'll spread it across a number of physical machines. Each machine can then take part of that influx of load and make a decision about dropping or not for each individual packet. You can do that, these sorts of filtering you can do on the router using an absolutely hideous thing called FlowSpec, which allows you to write some very rough rules about how to drop something. This is one here saying, we're going to discard any packet to this IP address that's DNS and has this particular packet length, which sometimes is useful. In this case, a 1,500 byte incoming DNS request would look a bit odd to us. But it's very, very coarse-grained. And you can't do any inspection. You can't look inside. It's just that long. So at the other end, right down in the actual DNS server, we can do about 300K packet per second dropping, because there you're actually doing the full parsing of DNS, and you can do whatever you want, right? You've got the full payload and you can make a decision. So you can make a very fine-grained decision about what to drop, but at a very low rate. when you're under attack. So what you need is some tools in between. You need something that's a bit more fine-grained but can deal with large packet floods. Part of the problem with the DNS server is that in some ways the Linux network stack is slow. Now it isn't slow for most workloads, but when you're under 10 million packets per second it can be. And realistically, once a packet has made it all the way into the DNS server and been parsed, dropping it doesn't do much. You've done all the work, right? The CPU has been burnt, parsing it, it's been moved into memory, it's gone through kernel boundaries and all sorts of things. So we had some rules, but honestly we've actually removed them. They were ineffective. So what you really want to do is use some kernel functionality or use functionality of cards like Solarflare. So one of the things we do is we use a thing called BPF, which is the Berkeley Packet Filter, in IP tables in the Linux kernel. And we can do about 1.2 million packets per second doing that. And what's nice about this is it allows us to inspect the full payload without doing complete parsing of the packet. And so the way in which that works is, so Berkeley Packet Filter gives you essentially an assembly language, which you can write rules to inspect a packet that's in memory, and it creates a bytecode. And so you literally get an IP tables that looks something like this, which is, all the UDP coming to port 53, run this BPF, and here's the bytecode. And if that bytecode says yay, then drop the packet. And so this actually ends up getting jittered and put into the kernel, and is very, very fast. And if you wanted to know what that code did, you could actually disassemble it. We have some tools that are all open source that actually generate this stuff, and this is what it looks like. What this is actually doing is it is looking for any DNS packet that contains a query in the form something.example.com. So it's able to actually parse the packet and drop it. And because it's done in the kernel, it happens very, very quickly. And we have tools, and you can get them from our GitHub that allow you to write this sort of stuff. The tools actually give you various sorts of different matching based on the sorts of attacks we see against DNS. There are similar things you can do for SYN floods and other things like that. IP tables, nevertheless, is relatively slow. 1.2 million packets per second is still fairly slow. Remember that the 10 million packets per second is coming in, is being spread across some servers, but we can't afford to burn the CPU doing this BPF stuff all the time, so we need something in the middle. And the thing in the middle is a thing we call Floodgate, and this allows us to take a stream of packets hitting a machine, and what we're doing is we ask the Solarflare card to direct that stream. So let's say direct all of the DNS to a particular receive queue in user space, so bypass the kernel, and actually steered to an individual core in the machine as well. So you get locality of the stream. The stream goes from the card to a particular core. And typically can stay actually inside the cache in the CPU. So you're not even actually having to copy the packet into memory unless you want it, right? So this thing, Floodgate, allows us to tell the Solarflare, there's a functionality you have on the Solarflare to say, this stuff, it goes over here, it gets handled separately. The other stuff goes up to normal NGINX, for example. And that allows us to do about 6 million packets per second, doing the BPF type rules, examining the full payload on a single core. So what happens in our machines, we'll have, say, 24 cores, and under a heavy attack, one core the attack gets steered to that core, and it just is used to make a decision. And then the 1 in 10,000 packets will insert back into the kernel and actually get handled. And so that allows us to essentially just deal with attacks without having any special hardware. Originally, the way we did this was we had S-flow data from our switches, we would aggregate it, there'd be a nice screen, and an operator would say, that looks really bad, and actually type in commands which got sent out to the network. That works, but you're relying on a human. It was making recommendations. It was essentially saying, launch these missiles, move that submarine or whatever around, but you still had to do it yourself. What we did was, the graph, we have these graphs internally that say, this many million packets per second hitting these locations, etc. But what we did, we completely automated it. So we now have this thing called Gatebot, which actually is a rules engine which looks at the S-flow data and says, aha, this is happening. I will automatically put in place IP tables, or I will automatically start Floodgate, depending on the packet rate. So if the packet rate is fairly low, we may let IP tables handle it. And as it ramps up, we'll say, right, it's going to get dropped by the Solarflare card directly using BPF. So we drop very large. The largest one recently we've seen was 100 million packets per second across the network. And this is just happening one core without disturbing the rest of the operation of the machine. So why did we end up using Solarflare? So we tested other things. We were originally using Intel cards. We're still doing experiments with Intel cards. We still want to find out where the best performance is. Packets per second per CPU, that was the biggest win for us. We can afford to burn 1 in 24 cores to deal with an attack. The software is open. There's good APIs. We're able to innovate. We're not locked into it. Loads of options. The thing I described with traffic steering to the particular CPU, that's very, very important for us because we can separate things out. And this has completely eliminated the need for us to have scrubbing boxes, gigantic machines that have to do packet scrubbing. And the reason that was important for us is they become a single point of failure. What we're able to do is spread any attack across our infrastructure. And bear in mind, this is all running on the same machine that's running our DNS server, that's running the NGINX server, that is serving up content to end users. So really, with Solarflare, this has allowed us to do that. And most of the code is on our GitHub if you want to get it. And I think that's it for me. Thank you. All right, are there questions you want to ask either of us?
So we have time for some questions?
Yeah, I think we do. Yeah, we have a few minutes. Anybody got questions about Solarflare or what we do with NGINX or BPFs or anything like that? Yes?
Load balance with
So the question was, how do we load balance with Anycast between the POPs? So, I mean, the simple answer, of course, is that BGP is doing it for us, right? So we're advertising the same IPs around the world. The slightly more complex answer is there's a team of guys who are looking at the routing constantly around the internet and deciding, okay, where should we be peered, who should we be connecting to, and where should we be advertising what? Because for some geographies, for example, the US, it's fairly easy just to use BGP Anycast. There's good connectivity, the networks are stable, stuff that kind of works. The opposite extreme is China, where we have a big network, where it is almost impossible to use Anycast at all, and we actually use Unicast there and have a whole thing in our DNS server which is balancing stuff across China. And then there are other regions where you might find in South America that Anycast works really well within the region, but globally doesn't work so well. So it's really a question of traffic engineering and deciding, okay, this gets sent out here or not, depending on the region in the world. You got anything else?
I've got a question for John.
Yeah.
There seemed to be an exponential curve on how big the DDoS attacks are. They were like at 40 to 100 to 400 gigs. So how's CloudFlare going to keep up next year?
Well, we keep buying more Solarflare cards, right? And no, realistically, I mean, it's asymmetric, right? I mean, you can get a lot of machines to launch an attack. I mean, that's fairly easy. So, you know, as connection speeds go up, as there are more and more machines with good NICs in them, the speeds will just go up. You know, I think to a certain extent, if Ethernet stopped getting faster, the attacks will stop getting faster. So, I mean, we're just in the same, it's almost an all boats rise thing, right? So it sounds dramatic that it's 400 gigabits per second or whatever, but our aggregate capacity is terabits per second. So, you know, it's actually probably, if you graphed it out, fairly static if you divided the two things together. Yes? Yes?
So you monitor your availability with Anycast?
You mean like our website, like where the websites are operating on us in terms of availability? I mean, we use a bunch of commercial tools. So there's a bunch of different things out there, Thousand Eyes, Catchpoint. There's a lot of reporting tools like that where we look at to see what connectivity we've got. And because we have Unicast IPs as well and all these POPs, we can test the connectivity to everywhere as well. So we operate both an Anycast public network and a Unicast private network. So we have connectivity to all the machines. I think we have, yes. Do I use what? I don't think we do, no. I just asked one of the SRE team because they may be, but yeah. We use it for, so the question was about RUM. So from a we have a thing which beacons RAM information into us, and the goal is for our end customer to be able to see, from my website, I'm getting this kind of thing. Right now, we don't use RAM to monitor the network because we have a lot of other tools just for, but we do want to, because we reach pretty much the entire population of the internet every day because of the scope. So we should be able to see connectivity, and we have the data, we just haven't yet started digging into it to understand, okay, this mobile network in the Philippines is worse than this one, and the data's there. We will do.
Any more questions?
All right, thank you very much.
Thank you very much.